Thank you very much for the kind introduction and for having me. So this talk is on system infrastructure for data-centric ML pipelines. So let's talk about what is a data-centric ML pipeline. You're probably well familiar with a classical ML pipeline that is composed of typical feature matrices and labels, either numeric or categorical, fed in. And then we have an iterative training process. And once you're trained a model out of that, you use that for scoring, for making predictions, and you get a certain accuracy. Now, typically, those kinds of training and scoring procedures, they're used in a number of popular machine learning libraries. So we encapsulate that into a training and a prediction procedure. Now, ML pipelines typically also include some form of data preparation where we get our structured input data sets and bring them into a numerical representation to actually then run those entire pipelines over. However, the typical exploratory data science process also includes a number of additional steps. This includes hyperparameter tuning, cross-validation, but also model and feature selection, so classical AutoML. Now, data-centric ML pipelines add additional outer loops to those pipelines, essentially dealing with data integration, cleaning, but also data programming and data augmentation. So how can we take a small labeled training data set and synthetically generate additional examples in order to provide a better coverage over the entire data space. Now, after we actually went through this training process, there's also a lot of data validation, debugging happening all the way until we can actually deploy those models in production. Now, as you see, those additional outer loops, they now touch on key data properties and essentially create a deeper hierarchy of ML pipelines that we are executing. So we also did some work in the surroundings of the core training. So one work I will talk a little bit about is SliceLine from Svetlana, who was my first master's student at TU Graz, where we essentially try to identify effectively what are data slices in terms of conjunctions of attributes, where our model, instead of 85% accuracy, maybe has just 55% accuracy, which allows us to then find additional examples. Recently, we also have done some work on task parallel feature transformations in order to make especially repeated data preparation with different hyperparameters in the context of feature engineering much more efficient. Recent work also touches upon how we can actually automatically enumerate data cleaning pipelines and essentially apply hyperparameter tuning to the strongly data-dependent parameters of those data cleaning pipelines. And very recently, we also look more and more into the space of data engineering. With works of taking custom examples of custom data formats and automatically generating efficient readers, as well as how we can perform multimodal or alignment of multiple modalities. So we've done quite a number of use cases where you have multiple video streams, irregular time series, additional structured input data, and especially with varying frame rates in the videos, there are fundamental alignment problems. And how can we actually first align in order to then encode and use it for machine learning? Now, a key observation in this overall context of data-centric ML pipelines is that state-of-the-art data engineering in terms of data cleaning, data integration, but also specialized tasks such as semantic type detection, they are themselves based on machine learning. So it makes perfect sense to actually build those abstractions as a hierarchy of primitives on top of machine learning systems. Now, in this talk, I want to also make a case for a strong need of data independence for those data-centric ML pipelines. So there are a couple of directions where we currently see increasing specialization. In terms of data representations, so we are dealing with dense, sparse, compressed matrices, and sparsity exploitation is really one of the mega trends, all the way from algorithms where we include the one norm or the number of non-zeros in the loss function and learn sparsity patterns and the weights, all the way down to hardware accelerators, where recent GPU devices have dedicated techniques to also push sparsity further down to the accelerators. Second, we have specialization in terms of data placement, where depending on the workload, you want to run things locally or in a distributed manner, or leverage different hardware accelerators with trade-offs of reconfigurability, energy efficiency, and performance. Furthermore, recently, there's a surge of new specialized data types that have different width and combine different precision, but also range of values that we can encode with them. And finally, we are dealing with a variety of different data modalities, including structured data, time series, videos, images, speech, and essentially all those different forms of specialization make it more harder to actually automatically generate efficient execution plans for those already very complex data-centric ML pipelines. So we can learn from the database literature and trying to aim for data independence. So already the seminal Ted Cott paper, essentially one of the main goals in there was to decouple the applications from the underlying data representation in terms of ordering, the existence of index structures, and with that, essentially what kind of access path the system chooses to access certain data points. So I will come back to data independence by showing a couple of existing works. Before we go into those different systems, a little bit about language abstractions and APIs. Later I will talk a little bit about the evolution of SystemDS and how it originated from SystemML. So SystemML provided a domain-specific language with R-like syntax in order to write new or customize existing machine learning algorithms. However, in practice, the majority of people actually mostly calls existing primitives in terms of algorithms and techniques for hyperpyramidal tuning. So what we envision is a hierarchy of primitives that can themselves be implemented in such domain-specific languages. So for example, this %* here represents a matrix multiply, which is inherited from R, where % is the ability to create an infix operator. So custom operators and the matrix package define the matrix multiplication like that. But now we can build essentially, so we can wrap those scripts in a domain-specific language into functions and compose larger hierarchies. So we have a hierarchy of algorithms that might dispatch based on certain characteristics, which is the better suited logical algorithms. But then also build higher level abstractions. So here we see an example of a forward selection, feature selection method called stepwise linear regression, where we have an input feature matrix. We probe the individual features, learn individual models, take the most predictive one, and then in an outer loop, we go over the remaining features and we run what if analysis. What if I take this, and this feature, append it, build a model, what would be the improvement that we are getting. And on top of that, we envision essentially user scripts that primarily leverage those higher level primitives for their actual workloads they're having. Now, a key aspect to recognize here is that those domain-specific languages try to provide a separation of concerns. So we are dealing with logical operations, a matrix multiply, not a local or distributed matrix multiply, and abstract data types, a matrix, not a sparse, dense, compressed matrix. And this separation of concern allows people to labor on their logical algorithms and system infrastructure underneath to actually exploit the actual workload characteristics in order to efficiently execute those logical representations. Now, that brings me to the architecture of previously SystemML, now called Apache SystemDS. So SystemDS takes those high-level DML scripts and goes through an optimizing compiler that generates hybrid runtime plans of local in-memory operations and distributed operations on frameworks such as Apache Spark. Now, the history is that Apache SystemML has been started around 2009. Actual implementation started 2010 as a proprietary product at IBM Almaden, and with involvement from TJ Watson Lab as well. And then at Spark Summit 2015, here's an image of Beth Smith, the general manager for software development at IBM, essentially announcing that we open source SystemML. I was actually sitting in the room there. And then we entered the Apache incubator process 2015, became a top-level Apache project in 2017. When I took over my group 4 years ago at TU Graz, we forked this open source system and refocused on the end-to-end data science lifecycle, renamed it to SystemDS, and later were invited to actually take what we developed in our own repositories and merge it back into Apache SystemML. And that's when Apache SystemDS actually came, and still the main umbrella project of my group, where as our individual researchers, PhD students, undergraduate students, and postdocs develop their research, they live actually integrate this on the fly. So we're not holding anything back. It immediately ends up in open source. Now, over the years, we added additional backends. In 2014, when deep neural networks became more and more common, we essentially added those accelerator backends. And recently, in the last 3 years, we added a dedicated backend for federated learning, and I have a couple of slides on it, both for federated parameter servers, which is the predominant architecture that you will see in mainstream research, but also for general linear algebra programs, which actually allows us to take this entire hierarchy of primitives and automatically compile this into federated runtime plans as well. Now, a key lesson we learned in this process is that this data independence, and that's the first case of data independence I want to make, between the algorithms and the underlying execution plans is extremely valuable because technology and frameworks come and go, and decoupling the algorithms protects the investment we are making into those primitives, while essentially separating the effort of adding additional backend. So this gives a lot of flexibility. All right, now that's the high-level architecture. You're probably wondering, yeah, but how does it actually happen? So I have a toy example, a closed-form linear regression, where I walk you through how we actually compile those execution plans. So given the script that essentially reads a feature matrix X and Y, if intercept is required as a user parameter, then we append a constant column of ones that allows us to compute essentially a shift of this hyperplane, learning one particular weight for it. And then we compute two main matrix multiplies, an XTX and XTY, that creates a feature by one set of normal equations, so relatively small, that we then actually feed into a solver. So those two main matrix multiplies, they are actually the key where we spend execution time. Now, our optimizing compiler takes those high-level scripts, parses them into a hierarchy of statement blocks and statements, and the conditional control flow delineates essentially where those individual blocks are. Per last level program block, we are then compiling DAGs, or directed acyclic graphs of high-level operators. So those high-level operators have names like BA plus star, binary aggregate. The outer operation is a plus, the inner operation a multiply. So this is a matrix multiply. And you have an R T, which is a reorg operation transposition. Now, we take metadata from the inputs, and in our case, we have 100 million by 1000 input feature matrix, dense, so 800 gigabytes. We take those dimension informations and propagate them through the entire conditional control flow, and then bottom up through the entire DAG. So in such a DAG, the individual nodes are operations, the edges are data dependencies, and essentially the output of an operation also represents an intermediate result. Now we take those dimension information and we propagate them bottom up through those DAGs. Based on this dimension information, we can then compute memory estimates. What would be the pinned size in memory if we were to execute this locally, which requires to essentially pin the inputs, pre-allocate the output, and keep all that simultaneously in memory. And then we can compare those memory estimates against our cluster configuration, where we have potentially a driver memory of 20 gigabytes here. And then in a very fine-grained manner, actually select local versus distributed operations for those individual operations. Now, once we selected the execution type, we then, similar to database management systems, select, depending on the characteristics that we are about to process, different physical operators for the different logical operators. So, for example, for matrix multiply, we have like 7 different physical operators for our distributed operations. So in this particular case, just for the sub-DAG that I have the dashed line around there, we are compiling a map-MM, which is a broadcast-based matrix multiply that essentially broadcasts the small vector and reads in a data local manner in a square tiled representation, the main matrix in a completely data local manner. So if it's already sitting in aggregated memory of your Spark cluster, it just scans it from main memory, takes the broadcast vector, computes local matrix multiplies, puts the output out. Then there is a pure partition aggregation happening that is locally in each executor, and then there's a global aggregation happening. Similarly, for this XTX, that's a self-join, if the number of columns is less than the block size, we can actually just stream in blocks and compute a matrix multiply with the block itself, and then again output partial aggregates and let the framework do its job. So that way, we essentially have 2 scans of the matrix, completely data local, partial aggregation on locally, and then some global aggregation happening. So this works great. It relies on a couple of key aspects, which is size propagation, which is challenging, especially for sparsity. We need to estimate memory in a worst case manner, because if we schedule operations into local runtime, we need to guarantee that we are not running out of memory. The different runtimes need to be tightly integrated, that we have efficient data transfer between the different backends. Due to conditional control flow, often, especially for complex function call graphs, this is not possible during compilation time to fully infer all those intermediate sizes and characteristics. So there we heavily rely on dynamic recompilation, which is an extremely important feature for JIT compilation, where we essentially on natural blocking points in between those statement blocks, we keep the original high-level operator DAGs around, take out of the simple table the actual size of intermediates, push them again into the leaf nodes, and dynamically during runtime recompile essentially execution plans. And usually in normal DAGs, 50 to 200 operators, dynamic recompilation is in the order of sub-milliseconds, which is not too much overhead, even if you only execute local operations, but we only do that if there's at least one distributed operation. And if we get rid of that unnecessary distributed operation, there's a huge benefit. If we anyway execute this large-scale distributed operation, then usually we anyway have a latency of 10 to 100 milliseconds of execution time spawning those jobs. All right, now this is the basic compilation, and of course there's lots of additional techniques and optimization passes. I just want to highlight a couple of things related to rewrites that we're all familiar with from classical rewrite systems in database systems before we actually come to a cost-based plan generation. So we apply a mixture of traditional programming language compilation techniques such as composite, threshold elimination, branch removal, constant folding. And a key observation there is that sometimes relatively complex programs actually beautifully collapse, where some of those techniques are enablers for other rewrites to trigger and apply. So for example, once we've done constant folding into the actual conditions of branches, sometimes they become true or false. So a false branch, you can completely remove this entire branch. And if it was somewhat conditional data modifications, suddenly once you remove that branch, the size is purely linearly propagate through, and you can actually estimate afterwards and do other simplification rewrites. To give you a few examples, all of which actually came out of real scripts that we encountered in practice, working with various use cases. So the first rewrite is a trace over a matrix multiply. So assume two squared matrices, matrix multiply, cubic complexity, and you take the trace, which is you take all the elements from the diagonal and you simply sum them up. Now, this is a lot of wasteful computation. So everything that's read there is actually totally unnecessarily computed. So as it turns out, instead of computing the full matrix multiply, we can just turn around one of those matrices because we're only interested in where the columns match on the diagonal. So we turn them around and compute an element-wise multiply and then a full sum over them, which changes the asymptotic complexity from cubic to squared, which is, of course, giving us a lot of benefit if you have relatively large matrices. Other rewrites are more mundane. So you see, for example, this sum lambda times some matrix, where the scalar scaling of this matrix allocates another matrix, and the read from memory right into memory, and the actual allocation consumes way more time than the actual operations. So there, you want to pull this multiplication essentially out of the sum, compute the sum, and then simply scale the entire quantity. Those are static rewrites, which is basic pattern matching. But given the sizes that we inferred, we can utilize those sizes to also apply dynamic rewrites that have additional constraints on them. So, for example, a common operation that you will see is the sum of x element-wise squared. So for every element in this matrix, we square the value and create an equal-sized matrix in terms of dimensions. Now, if the matrix is just a vector, you get a fused operator that does not allocate this element-wise output by simply doing a matrix multiply with itself. So it's the vector in and the matrix multiply does the essentially squaring with itself and at the same time the sum. Other rewrites are, for example, matrix multiplication chain optimization. So matrix multiply is associative. We can't arbitrarily reorder them, but we can select the optimal parentization. So in this example, we have two squared matrices and a vector. If we apply them like on the left-hand side, we get 2 gigaflops for dense inputs. However, if we set the parentheses differently to perform first the matrix vector, giving us a vector, and then the second matrix vector, we have almost 3 orders of magnitudes reduced number of floating point operations. So in this context, we also did work on better and more cost-effective sparsity estimation and how we can propagate those sketches through entire DAGs of operations. And then prototypically, not implemented in our system yet, essentially also extended those classic textbook dynamic programming algorithms for matrix multiplication chain optimization to propagate simultaneously our sketches through. There, it's still to be integrated when it actually, well, the overhead of creating those sketches, propagating them, actually, although they were efficient in the order of the number of the sizes of the dimensions, there's still cases where this can actually create additional overhead. So actually doing an effective integration is still an open challenge there. All right, now coming to the SystemDS architecture. So while morphing it from SystemML into SystemDS, we added quite a number of new features, including new language bindings to better plug into existing data science workflows. So you can actually do a pip install SystemDS, and you can nicely use our Python API with lazy evaluation that essentially collects larger DAGs of operations. Once we come to an operation or to an explicit compute similar to Dask, we take all those operations, compile a script, and then it goes through the exact same optimizing compilation chain. Then we added a large number of new built-in functions in order to build up essentially the stack of primitives that users can directly call instead of implementing their own algorithms. And then a couple of new features really include lineage-based reuse. I will talk about this, new backends for federated learning, and really a new library for different value types and generalization to tensors. But this also includes really which is not completed yet, but it also includes a new data abstractions specifically for workload-aware compression. And I will talk a little bit about it. And we are actually, meanwhile, very proud that building such an optimizing compiler and runtime system is really takes a village of people. And initially, you face a lot of really difficult bugs where it's almost annoying for a user working with such an early system. But meanwhile, we actually built quite an impressive test suite of more than 100,000 actually test cases, and those are not values we are comparing, but actual test cases, and out of which more than 8,000 actual DSL scripts, including various algorithms, various configurations, and things that we run on every commit in our GitHub repository, and really ensuring that there are not too many regressions. All right, in the next couple of slides, I will first show two examples of advanced built-in functions we've been working on. And then we go more in the system internals and talk about a couple of those selected research projects we did in this context. So the first higher-level primitive is this automatic enumeration of data cleaning pipelines. So Shafak did a great job in actually building a robust parameterized library of those data cleaning primitives. And just to give a few examples, so for example, there is a cleaning primitive for imputation, so missing value imputation by robust functional dependencies. So you can clean from the data if there is a functional dependency. So whenever we see Graz, the country should be Germany. But often with data errors, you get something like 90% of all the values adhere to the right-hand side of the functional dependency. Once you determine that, you can then use the majority vote to actually clean the remaining instances. Now, this heavily depends on this threshold, how large we set this threshold, and this is highly data dependent. Other cleaning primitives are mice for, again, missing value imputation. So what it does is it assumes correlation between independent features, extracts columns where we have missing values in it. We take all the observed values as the training data set. The other independent features now become the features. This becomes our new label. Actually, if categorical data, we train a classifier, numerical data, we train a regressor. Then with that learned model, impute the missing values and go to the next column with missing values and do that repeatedly until we reach a fixed point where not a lot of values are changing anymore. Now, given an input machine learning application, we then use an evolutionary algorithm to actually compose data cleaning pipelines, so to order them, to select which primitives to use, and then use modified versions of hyperbands. And initially, we also use Bayesian optimization, but meanwhile, it's really a bandit-based representation to tune the physical properties in terms of the hyperparameters of those cleaning techniques, and then show the user the top K cleaning primitives. And what differentiates this framework is that we are really automatically compiling this into data and task parallel computation. So if you have relatively small data, we run a lot of pipelines concurrently. If you have large data, we automatically compile large distributed data parallel computation plans for them as well. So that's the data cleaning pipelines. On the model debugging side, we've been working on SliceLine, where there was previous work, SliceFinder, and a couple of other works that are related in terms of data coverage. We introduced and contributed essentially this intuitive scoring function. So what we aim to achieve is to find the top K worst slices, where slice is a conjunction of attributes such as gender female and degree PhD, where our model performs significantly worse than on average, potentially because this slice is underrepresented and we should acquire more data, we should add rules or otherwise improve the model. Now this Pardon me. So this intuitive scoring function essentially trades off slice errors and slice sizes, and it has a couple of very compelling properties, such as if a slice is half as large as the original data, but has twice the error, it has exactly the same score. It's also perfectly balanced under this tuning parameter alpha. And additionally, we establish a minimum support threshold, which allows us to exactly enumerate the exponentially large lattice of potential distinct value combinations. So how we do that is we observe there, we can exploit essentially monotonicity that, similar to frequent item set mining, exploits the a priori property that a slice can only be frequent if all its subsets are also frequent. So female and PhD can only be frequent if female is frequent and if PhD is frequent. Otherwise, we can prune essentially all reachable subnodes. And the nice and compelling property in those lattices is that as you descend to lower levels, the number of parents increases, which increases the pruning power because it's an extreme value. So it's the minimum of all the parents that we compare against this threshold. And then we formulated this entire enumeration problem in linear algebra, such that we can actually execute this with the exact same infrastructure for local and distributed operations on SystemDS. The way how we do that is we enumerate an entire level in this lattice with a single matrix multiplier, where we enumerated candidate slices with pruning and encode our matrix in one hot encoded form. Here we have two features, red and black, and the individual values are one hot encoded, and matrix multiplying them together gives us on the output, integer values that represent how many predicates for a particular slice actually matched for this particular tuple. And that can be compared to the level. So for level 2, 2 predicates have to match. For level 3, 3 predicates have to match. And that way you can actually then really leverage this entire infrastructure. A second major technique, and that again goes now, or are there any questions? I should not too quickly brush over it. If there are questions, I can answer, otherwise we do it later.
Any questions, either from the room or online? No questions for the moment. Maybe one question about, so I mean, in some of those approaches, I mean, you are using essentially cost-based optimization. And I think you already mentioned quickly that, for instance, size estimation can be sometimes challenging in this context. I mean, I know from traditional query optimization, it already is often quite challenging, and there we have a more restricted scenario in certain ways. So can you comment a little bit whether that is a problem in practice, or whether that's, it seems that it's working actually very well. So I'm curious to hear a little bit more about that.
So some aspects are actually easier and other aspects are more difficult. So dimensions is actually a very structured problem. So if I have two inputs in the matrix multiply, the dimensions are specified by the rows in the left-hand side input and the columns in the right-hand side input. And that perfectly propagates recursively through those stacks. Now, sparsity is as challenging as cardinality estimation, but there are a couple of good estimators, and our MNC estimator, whose ideas, meanwhile, actually also have been, similar ideas have now been applied in the last 2 or 3 years at our major conference for cardinality estimation. So there are similarities, and because you can represent a join, if you assume a matrix in triple representation, row index, column index, value, then a matrix multiply is actually a group by over a join, and hence similar estimation techniques actually apply, which is very compelling. And for us, right now, it's a good trade-off that's to infer sparsity wherever we can with basic metadata estimators and rely on dynamic recompilation to then, after conditional control flow, when things really changed, to then get the exact sizes after we allocate it. But that for intermediate still has challenges. And now in the next 5 to 10 years, we will see a more and more specialization toward efficient ML, where people try to be more resource friendly by learning sparsity in the weights, learning sparsity in the actual input data, and combining that with other techniques such as feature selection. And there you get changing sparsity over the entire course of the application, and not just sparsity, but also sparsity patterns. So some people impose block structures to still make it efficient on hardware accelerators. So that will add additional challenges, and we should think about additional work in this space. Absolutely. And I think there are still remaining problems, actually, how to fully integrate it there. But excellent question. All right, then I would continue with a couple of internals. And if you're running out of time, you can just cut me off. They are rather independent works, but I think they give a nice holistic view. So the second case for data independence is if you're building up those larger and larger hierarchies of built-in operations, computational redundancy is inevitable because in this larger stack of things we are trying to reuse, there are unnecessary operations for its actual use in any of those particular primitives. So we integrated natively actual lineage into our system for multiple purposes, one for debugging and for being able to reproduce intermediate results. But obtaining this lineage graph and keeping all the information to, given the same input data, exactly reproduce the exact intermediate that requires obtaining system-generated seeds and all sorts of other variability. Once we have this ability, the lineage uniquely identifies a particular computed intermediate. So we use that actually in a reuse cache and support full and partial reuse. So imagine a simple grid search. Here we have, again, this basic LM model. We feed different regularization parameters lambda in it. So at the surface, it looks like there's no reuse potential at all. But once we let the optimizing compiler break down those abstractions, we see that the regularization parameter does not impact those two matrix multipliers. So we execute them once and reuse them for all the other invocations in a hyperparameter tuning. And with that, change the asymptotic behavior. Furthermore, I introduced this stepwise linear regression. There, we repeatedly train models and then append additional columns. So a key observation is that in the previous iteration, we already computed most of the intermediates, except for compensations, and this is similar to compensations in materialized views, where we reuse a materialized view and then compute compensation plans on top of that to produce the actual result. And with that, similarly, can change the asymptotic behavior. So that targets computational redundancy. A second case I want to make is data redundancy. So in the past, we had work on lossless matrix compression, where we essentially applied column-wise lightweight database compression schemes to numeric matrices, and then run linear algebra directly on the compressed representation. So a simple example is this DDC scheme, for example, which is a dense dictionary coding, where we simply take the distinct values, create a dictionary, and then encode every value as the position in the dictionary. Additionally, we also perform co-coding, so that way an entire tuple of multiple columns can be represented as a single code in the dictionary, and the dictionary stores the distinct tuples, so combinations of values, which can be still very small if there's a lot of correlation between different structured attributes. And we see this, although the mainstream compression in deep neural networks is essentially performing quantization and similar techniques, so lossy compression. We believe that lossless compression has much more additional potential that's untapped yet. And for us, this is a generalization from sparsity exploitation, which is currently a mega trend, to more general redundancy exploitation. So if we think about those pre-processing pipelines, missing imputation by mean or mode introduces constant values in a lot of different fields, and eliminating this redundancy while preserving and guaranteeing that we can compute the exact same result, which is otherwise a trial and error process, which which becomes more and more problematic in those deeply structured data-centric ML pipelines, is actually very valuable. So in this earlier this year accepted Sigma 23 paper, we essentially introduced then a workload-aware compression, where Sebastian really extended the number of compression schemes, ways how we can also keep intermediates compressed, not just the main feature matrix. And we made a profound observation that many frameworks that aim for compression try to improve the compression ratios, but that alone is not useful. So what we actually aim for is to minimize execution time. So if our matrix comfortably fits into available memory, then we should aim for improved performance and select compression schemes and strategies accordingly. If we have very large matrices that fall out of aggregated memory and in every iteration we have to read them in, there the compression should automatically prefer better compression ratios. So we do this compression by actually utilizing the information of our compiler, seeing all the operations we want to execute, and for this on-the-fly compression, then utilize this workload summary and compress it accordingly in order to reduce cost. And vice versa, once we have this compressed representation, we introduce this information into the execution planning. So once we compress a matrix, distributed operations might no longer be necessary, and we can actually compile local operations. So it affects memory estimates. So that's data independence number 3. This decoupling essentially allows us to do that kind of data reorganization automatically under the covers, which would be very hard in a hard-coded library where the user has to choose between compressed and essentially uncompressed operations. The fourth case of data independence is our federated learning backend. So here we support new federated data objects, which are essentially metadata objects where, so federated learning, sorry for not introducing it, aims to train models without central data consolidation for data ownership, data privacy requirements. Now, most existing work adopts a classical pyramid server architecture. Now, instead of having pyramid servers and workers, where the workers hold data partitions, we initialize a global model, send it to the workers. Now, for example, mobile devices, they perform a forward-backward pass through a neural network to compute gradients, and we only exchange those aggregates. So besides federated pyramid servers, we support general federated linear algebra programs. And the way how we do that is to introduce those federated data objects that are essentially metadata objects that say, for example, certain row partitions are physically located on particular federated sites. So in this project, we were working with Siemens and actual paper production sites, or use cases out of paper production, where the scenario is you have a handful of production sites. They don't want to share data, but they are allowed in this overseen infrastructure where there's still encrypted communication between kind of Siemens as the main consolidator and the individual production sites. They're willing to share aggregates. And so in those cases, whenever an operation actually touches this federated data object, we spawn additional, similar to distributed Spark data parallel operations, spawn operations to workers that physically run as servers at the federated sites, and then essentially for some operations can keep intermediates on the federated workers. For others, we have to do a full aggregation. So how we do that, and we support, meanwhile, it's really feature complete, and we incrementally improve robustness, performance, but it's pretty much for wherever it's possible to compile our built-in functions or in general scripts into federated runtime plans. We are able to do that. And the reason why we accomplished supporting all those different operations is kind of an abstraction where we introduced very few so-called federated requests, such as get a local data object, put it onto the federated site, get is the data exchange in the other direction, and high-level primitives such as executing an instruction that executes a local instruction on particular input datasets, which allows us to completely reuse all the instructions from our local backend. Yeah? All right, so in this context, we did then a couple of follow-up works on also supporting federated pre-processing in terms of feature transformations, but also a variety of our cleaning and preparation primitives. For some of those cleaning primitives, they required dedicated approaches where we had to really implement dedicated physical operators, for example, for federated quantiles, where normally a common approach is to sort your column and then pick at a certain position. If you have federated row partitions, you can't just sort, but there via recursive histograms, we can still essentially relatively efficiently compute those quantiles. Furthermore, we added tenant isolation to actually allow multiple data scientists to simultaneously work with those federated workers without overriding each other and peeking into the intermediates of other results. So there's a certain tenant isolation. They have their own maps of intermediates at the federated sites and a certain protocol between them. In this context, a key observation is, in contrast to traditional stateless machine learning systems that execute a certain workload and then are tiered down, those federated workers act actually as workers, long-running standing workers, and with that have similar characteristics like a database server that can asynchronously actually perform certain data reorganization. So the previous two projects on lineage-based reuse and compression were already integrated into this federated backend of, for example, allowing asynchronous compression, where we summarize the workload as it streams in and then trigger outside the critical path actually a compression and then utilize this compressed representation whenever available. So during COVID, we also had interesting experiments where one of my PhD students, we are running actually those multiple different traditional machine learning algorithms and neural networks from his laptop in Copenhagen, Denmark, and the servers that simulated the federated sites in Graz, so it's a distance of 1,500 kilometers, and we compared against local operations as kind of the lower bound, what how much overhead does it have, and varying the number of workers. And what we see is that both in a local LAN, but also this wide area network, Copenhagen, Graz, the overhead is actually very moderate, and with that, federated learning is actually very practical. In some instances, the federated learning with multiple workers actually outperforming local operations simply because we have more resources to available. And just as a validation, we also compared our local backend against common frameworks like scikit-learn and TensorFlow, where we see it's in the same ballpark. In some use cases, SystemDS is faster. In some use cases, TensorFlow and scikit-learn, but this is not log scale, but so in the order of up to 2x differences, which means those observations would also generalize to other systems. Since we started a little bit later, but I'm almost out of time here, so I will now quickly summarize the last project, DAPHNE, which is our second main umbrella project, but I only use 2 slides for that. So in general, what we want to support are integrated data analysis pipelines that or complex workflows of data management, high performance computing, and machine learning. And it's very interesting that those 3 areas over the last couple of years actually converged more and more in terms of the techniques they're using, the infrastructure they're using, yet there are often very different programming paradigms and often dedicated cluster infrastructure. And this dedicated cluster infrastructure leads to a spatial temporal underutilization of available hardware. Furthermore, in high-performance computing, for example, the state-of-the-art more and more also uses machine learning for approximating partial differential equations, even in things like fluid dynamics, material degradation, in order to make high-performance computing more cost-effective, or those kinds of simulations more effective. So what we aim to do with a great consortium is to build an open and extensible system infrastructure to support those integrated data analysis pipelines, which have now essentially also a combination of query processing, simulation, and machine learning in it. So recently we added to Berlin, so we are now also in the consortium, and the core of this architecture is a so-called vectorized tiled execution engine. And interestingly, the concept of federated data that I introduced nicely generalizes to heterogeneous devices as well, where we place essentially part of a larger data frame or matrix onto multiple devices, and then similar to vectorized query execution as pioneered in MonadDB X100, essentially take tasks for individual row partitions and stream them through essentially fused operator pipelines that allows us to minimize reads and write into main memory, allows us to keep those intermediates in caches and fully utilize heterogeneous workers, including multiple CPU workers and GPUs and FPGAs at the same time for certain operator pipelines. So the overall architecture is based on MLIR, so the multi-level intermediate representation, originally spurred by Google, now gets a lot of support actually from many different organizations and especially hardware vendors, because for them it is very compelling to provide own MLIR dialect for their hardware device, exposing the capabilities to which other systems can then lower to. And so for us, this really turned out quite nicely. There's a steep learning curve with MLIR because it can so much and is so customizable, but it really makes it more cost effective to build new domain-specific languages and utilize existing compiler infrastructure as a library. So in terms of existing optimization passes and just infrastructure that you otherwise have to build. And underneath, we are working again with our great partners on multiple different directions, including different hardware accelerators, FPGAs, GPUs, their joint usage, but also computational storage and how we push certain subsets of pipelines into the SSDs that have ARM or FPGAs on them, and essentially minimize data transfer. For example, if we perform quantization, it is ineffective to take a very precise representation, transfer them over to the CPU, perform the quantization that leads to a strong data reduction. So those are kinds of operations we really want to push down. And then we aim for extensibility. So by allowing new MLIR dialects and enabling researchers to really experiment with new data types and kernel scheduling algorithms, quickly plug them in and reusing this entire infrastructure. So that's, we are on our way toward extensible infrastructure with a couple of use cases of specialized data types, and I hope to make this really useful for other people as well. And since we're exactly on the hour here already, quick summary, we talked about data-centric ML pipelines and this increasing specialization, and with that increasing heterogeneity. And for us, the conclusion is really that optimizing compiler and runtime infrastructure becomes increasingly important in order to really deal with this increasing specialization. And that's pretty much what we will be doing with my group, at least for the next 5 years. So our two main research systems that we still try to make useful for multiple different levels of users are Apache SystemDS and DAPHNE, and we focus on integrated data analysis pipelines, so specialized for workload and hardware, automatic data reorganization in the internals, specializing for data, then data engineering pipelines and multimodal data sets, specializing often for a domain then, and finally deployment. So how can we specialize the runtime plans and the deployment essentially for the environment where we are in. And ultimately, it's all about finding the right abstractions, properly implementing those abstractions. And as I always tell my team, it's also about interdisciplinary collaborations to keep ourselves grounded. And on the top right, quick announcement. So we currently have 2 open job postings with application deadlines December 9th and 16th. So 2 PhD positions, one on data-centric ML pipelines and the other in the context of DAPHNE. So if you have interest or context that might be interested, please send them our way. With that, thank you so much, and I'll take additional questions.